Hello everybody, it's tough time during COVID-19 and I hope you all are well. Today I'm going to talk about permeable ground seal, inflow alternation and scour control for headwater streams. And my name is Yoda Chen. I and Jiajun Wu complete this research together. We come from NPUSD SWC, National Pingtung University of Science and Technology, Department of Soil and Water Conservation in Taiwan. This is the outline of my presentation. It will cover 5 sections. In the beginning, let's take a look at the stream regulation. The stream regulation is part of watershed management that it is focused at gradient checking and stream flow stabilization. Generally, we use ground seal to check stream gradient, but sometimes local scour occurs and damages ground seals. On the other hand, conventional ground seal often separate the waterway. It will be harmful to the riparian eco-environment. While we are thinking about local scour problem, we find an unconventional ground seal with some permeability as this picture shown during a field survey. It was constructed by SWCB Soil and Water Conservation Bureau in Taiwan. We thought it may be the answer to the problem. So the objectives of this study is trying to assess the feasibility of permeable ground seal by a series of laboratory experiments. Previous studies. After the field survey, we start to search the mechanism of local scour, and we find tons of evidence point out that local scour was conducted by plunging flow. And the plunging flow is usually occurred due to the high flow of riverbed, just like this picture shows. And we also try to find solution to reduce extent of local scour. Wu et al. In 2014 suggests that by applying riprap or other dissipation methods, a toy of ground seal could directly reduce local scour. But these methods often require high demand for construction spaces. Therefore, we believe that improvement is still needed. So in these studies, we will focus on the alternation of scouring process, plunging flow impact, and the feasibility of permeable ground seals. Material and methods. Firstly, our experiment was conducted under clean water conditions using this semi-circular film. The flow rate and gradient were changeable, and considering the boundary effect, the data was measured at these sections. Therefore, every experiment provides 5 repeated sections. Data management was using this high-resolution electronic optical laser. We arranged this instrument in a 3-dimensional measuring framework to obtain the stream bed topography data we needed. And these were the ground seal models we used, always just trimming the top 1 cm section of conventional models and replacing like this. The conventional type is non-permeable ground seal. It's commonly used in practical engineering. The second one is Type A model, which demonstrates a high permeability. It's formed by a series of ice covers, and it is made by PE corrugated board. The last one is Type B model, which imitates the one that we found during the field survey in Taiwan. It demonstrates a low permeability one. In order to know the characteristics of these models, we designed the experiment condition like this. And according to the previous studies, we know that local scour extent was controlled by these 3 main factors. Undoubtedly, stream power is the main factor to affect local scour extent. The equation we used was recommended by Bagnall in 1966, which involved density, gravity, flow rate, and slope gradient to express the force of flow. And we used median segment size to express the bedrock material. The permeability was quantified from light penetrating method. Every experiment consists of variables with 3 levels of magnitude. Because our experiment was conducted in laboratory, so we reduced the scale for 50 times, and the full similarity law was followed. The comparison between the scale model and prototype was shown in this table. Now I'm going to talk about experiment procedures. We prepare the bedrock material at the beginning of the experiment. Then we obtain the elevation data at top of ground seal and use bedform surface as a data. After that, we turn on the flow supply and record the video from different angles. We measure the water depth during the experiment for subsequent analysis like water head, average velocity, or flow number. We turn off the water supply when the bedform becomes stable. The time duration was between 1 to 2 hours, and it is depend on the testing conditions. Then we measure the bed elevation and toy of ground seal or any other positions for outline the bedform profile. All the data we obtained during the experiment has been transformed to a number. Then the number is about scour hole characteristics like average daytime surface elevation, the length of local scour, we call it lambda s, the depth of maximum local scour, we call it ys, and the distance between the lambda s and ground seals, we call it lambda m. This number allows us to investigate the variation of local scour extent, like this picture shows, or conduct further analysis. The following section is our research result. It will cover the effect of local scour control, energy dissipation, and regression analysis. Let's check it out. We transform the data from 81 experiments into box and whisker plots using quartile method. For the maximum of scour depth, ys, we find out a similar trend in those severe hydraulic conditions. While the hydraulic conditions turn into moderate, the disparity between different models become obvious. And for the comparison of the extent of local scour hole, we find a significant differences between type B model and other models. We wonder about the reason causing these differences. Therefore, let's look at the scouring process. This is a schematic diagram of conventional ground seal experiment. At the beginning, water coming from upstream area will silt at the backside of ground seal until it is completely full. Then the water plunge into the downstream section like waterfall. The plunging flow impacts the toy of ground seal concentratedly and produce a deep, huge, and flat scour holes. The following is the case of permeable ground seal. It is different from conventional one. When the flow contacts the backside of permeable ground seal, part of the flow will pass through the structure through the voids in the permeable ground seal like this picture shows. Because of this phenomenon, the quantity of plunging flow will decrease. On the other hand, this water will form a water film which could reduce the power of plunging flow as a cushion effect. Well, the next slide is about bedform diversity. It is another way which illustrates permeable ground seal can reduce the extent of local scour. And these three pictures were taken after the experiment with the conditions in 0.08 gradient, 1.05 mm sigma size, and 45 times 10 to minus 4 cmx. It produced a different bedform morphology, especially in type A case. We can see the uniform scour hole and depositing in the conventional ground seal. It is because the morphology of the conventional ground seal makes the water evenly distributed. Let's take a look at the type A models. It seems like the location of local scour will vary at different sections. It is because of the non-uniform clouding creates a gateway for flow to pass through. It affects downstream ground seals clouding continuously. And type B model perform more like a conventional one, but still have some judged bedform. The bedform diversity, which we treated as a roughness of bedform, can provide a dissipation effect and further reduce the extent of local scour. If we quantify the diversity as this picture shows, we can see that the bedform diversity is highly correlated with the ground seal permeability. This concludes our interpretation of ground seal permeability in scour extent reductions. The second part is energy dissipation analysis. we try to know how flow energy was dissipated by different Gaussian models. And the Darcy friction factor is used to refer the distribution of dissipation, which generates from platform morphology. And the friction head is a Helmholtz term in Bernoulli equation, which is head differences between total energy and the summarize of kinetic energy. We plot the result of Darcy friction factor analysis as the figure on the right-hand side. The vertical axis is a measure Darcy's friction factor. The horizontal axis represents the relative location between two adjacent ground seals. We find that Darcy friction factors possess high values within the extent of local scour. It is because of the dipole at the toe of ground seals. As the moderate hydraulic condition occur, another high Darcy friction zone appears at the extent of the deposit area. It is because of the backwater effect due to the reaction force. When the sediment fills the area during medium and severe hydraulic conditions, there is less energy dissipation. The figure at right-hand side is a comparison of friction head and distribution between different ground seal models at moderate, medium, and severe conditions. We find the energy loss uniformly distributed between ground seals, but the effect of energy dissipation varies at different conditions. For example, the type B model is the highest one at the moderate condition experiment. The type A model is the highest one at medium conditions. And similar result occurs for all ground seal models in severe conditions. I think these differences is produced in a complex reasons. In reason that type B model is the highest one in the moderate conditions, it is because all the voids in permeable ground seal is still functionable. But why is the type A having the highest permeability but present a low energy dissipation? It is because the voids of type A are too smooth to retard the flow. The reason that type A models is the highest one in medium condition, it is because part of the voids are still open, and the high bedform diversity is another reason. As for the similar result in severe condition, is because all the voids have been clogged, that make all models perform hydraulically close to non-permeable ground seals. The final part is the regression analysis. Through the hydraulic experiments and correlation analysis, we find that the characteristics of local scour were controlled by these four parameters. The flow rate and channel gradient represent the hydraulic erosivity. The sediment size represents the bedform erodibility, and permeability represents the ground seal characteristics. We use Buchan and Pyloride to achieve this dimensionless equation. To assess the usability of this dimensionless equation, we plot the measured ys over lambda s against the estimated result as the figure shows. This empirical equation is valid for the following prototype ranges. Conclusions. The first one conclusion is permeable ground seal are capable to reduce the local scour extent and alter the stream flow. The second one is ground seals with high permeability are not suitable to use in high gradient headwater current. It is because of the shooting flow effect. The third one is ground seal with low permeability are capable to reduce the local scour extent until the voids are clogged by sediment and low flow rate and medium channel gradient. The final one is the characteristics of permeable ground seal will affect the stream flow. Even after stream clogging, it still plays an influential role in local scour extent. That's all for my presentation today. If you have any questions, please let us know by email. I will be happy to discuss with you. Thanks for listening.